Welcome back. So we have yet another example here. Right here, this has to do with motion using rectangular coordinates. And here we have r defined for us as a function of time. So let's see how this works. It says a girl operates a radio-controlled model car. You can think of that as a remote-controlled car in a vacant parking lot. The girl's position is at the origin of the xy coordinate axis. So the girl is positioned at the origin of the coordinate axis, and the surface of the parking lot lies in the xy plane. So this is the xy plane. Now, don't be distracted by the fact that this doesn't look straight. Okay, we'll come back to talk about that shortly. So the motion of the car is defined by the position vector r equals 2 plus 2t squared I plus 6 plus t cubed j. So that means we have x as a function of time defined as this, and y as a function of time is defined as this. So that put together, this gives us r, the position vector of the body, as a function of time, where r and t are expressed in meters. So that tells us the units, so that when we get our results, we know the units in which we will express our results. And then s and t, r and t are expressed in meters and seconds respectively. So we have to determine a, the distance between the car and the girl when t equals 2 seconds, and b, the distance the car traveled in the interval from t equal to 0 to t equal to 2 seconds. So we're interested in distance traveled here, and c, the speed and direction of the car's velocity. That's like asking for the magnitude and direction of the car's velocity, because we know speed is magnitude of velocity, okay, at t equal to 2 seconds, and d, the magnitude of the car's acceleration at t equals 2 seconds. So we're given the position vector, and with that we want to obtain some velocity, speed, and also acceleration of the body. Okay, and again, let me quickly say that you should not be distracted by the fact that x and y here do not look straight. So we expect, for instance, that y should be vertical and this should be horizontal. Now, this is, I should look at this or see this or visualize this as a three-dimensional diagram where this is on the ground floor. Okay, this is the plane and this is up. So it's like this lady, this lady actually stands on this floor. The floor is where the xy plane lies. So it's like you have this axis here along where she stands, and this is like the z axis. This is x axis and this is y axis. So you can visualize it in that, wow, that's way. This is going to be that three-dimensional system. So this is still some axis that is perpendicular to this. Okay, just telling us that the way this girl stood or stands here, she is perpendicular to this because this is the ground floor as given in the problem statement. So the car is on the ground, this girl stands, and this car is on the ground as well. So it moves in this horizontal plane of the ground floor. All right, so that's what's important to us here. So let me just get rid of this that we just showed. Okay, so now let's get into analyzing the motion of this body of the car. As you can see, we know that the car is in the xy plane. So we're going to draw it right here as though we're just looking at the floor directly. So let's say we're just analyzing the floor, the motion of the car on the floor directly. So if this is the floor, this is our x-axis and this is our y-axis, then this is the location of the girl. Why? Because the problem statement tells us that the girl is located at the origin of the xy coordinate axis, and the surface of the parking lot lies in the xy plane. So this is the parking lot. This is the surface of the parking lot right here on the plane of this screen, and the girl is right here at the origin. So this is the position of the girl. And now the car will undergo some motion which is curvilinear because it has two components that vary with time. So this is going to be some curvilinear motion. We don't know the exact trajectory, but we know that is just going to be some curvilinear motion. Okay. This is not to say this is the exact trajectory, but just that we know then that r will be so defined as going from this point to that point. So this is our position vector r for an arbitrary location of the car. Okay, so that's what is important to us as far as this problem is concerned. So we can now go ahead to analyze this body. we have r already as a function of time, so we're given r, or r is known to be equal to, that is r as a function of time is 2 plus 2t squared I. So let's write it that way. So this is r as a function of time. We know it to be 2 plus 2t squared I. Then for the y components, we know that to be 6 plus t cubed j. So this is plus 6 plus t cubed j. And we know this is in meters. Okay, t is measured in seconds. So with this, we can get all of the parameters that we need. Okay, this has to do with t equal to 2 seconds. This has to do with t equal to um what is that, 0 seconds. So we also know that in this we will need the velocity, and also we will need the acceleration. So we can get the velocity vectors and also the velocity and acceleration vectors, okay, from here. So we know that the velocity vector as a function of time, that is going from this, we can get the velocity vector as a function of time. That will be the derivative of this with respect to time. We know that is the derivative of r as a function of time with respect to time. And so we can just differentiate this with respect to time. When we do that, the derivative of 2 is 0 because that is a constant. Derivative of 2t squared, that is 4t, okay, I, plus the derivative of 6, which is 0, then plus the derivative of t cubed, which is 3t squared, and that is j. We can also similarly obtain the acceleration vector. So acceleration as a function of time is obviously equal to the derivative of velocity as a function of time with respect to time. So derivative of this with respect to time, derivative of 4t, that is 4. So this is 4i. Derivative of 3t squared, that is 6t. So this gives us 6tj. And with that, we have the equations that we need, okay, at different points in analysis. So we will label these equations 1, 2, and 3. Of course, Roman figures 1, 2, and 3. So let us have an additional page here to proceed. Then let us see the first part of the problem. It says we should determine the distance between the car and the girl when t equals 2 seconds. Now, some English. Distance between a point and a point is simply the length of the straight line that goes from that point to the other. Okay, from the distance of the straight line between those 2 points. It is different from distance traveled. When we say distance traveled or distance covered by a body, that is the total length of the path followed by the body. In that case, we have to follow the trajectory of motion of the body to know and sum up all of the lengths, okay, the length of all of the paths followed by the body. However, when I say find the distance between point A and point B, that is just the length of the straight line that connects the 2 points. So when it says here that we should find the distance between the car and the girl, we do know that the girl is at the origin. So the distance between the car and the girl is simply the distance of the line we draw from the origin to the location of the body. That is simply the modulus of r. Okay, so let me repeat that. Distance between a point and a point is simply the length of the straight line between them. Distance is an English word, okay, normally, which just means some length, okay. So distance between one point and another point is simply the length of the straight line that connects those 2 points. Okay, that is different from distance traveled by a body in motion. If you want to get distance traveled by a body in motion, it means we will have to follow the path traveled. So it has to be the total length of the path traveled by the body. Okay, so that is clear. So we can see now that obviously, the distance traveled between the girl and the distance, sorry, between the car and the girl when t is equal to 2 seconds will be different from the distance traveled by the car by t equal to 2 seconds. So this is distance between 2 points. So we just pick the point where the girl is located, which is the origin, and connect it to the location of the body at this instance, so which is when t equal to 2 seconds. So let's go ahead and deal with that first part of the problem. So for the A part, we know that when t equals 2 seconds, the position of the body r at t equals 2 seconds will be given by this. So we just substitute t equal to 2 seconds here into our expression for r, and that gives us 2 plus 2 into t, which is 2 squared. Then we cover this and put I, then plus, so this is plus, we have 6 plus t cube, that is 6 plus 2 to the power of 3, and then that is j. So we can calculate this and put the result together. 2 squared is 4, 4 times 2 is 8, 8 plus 2 is 10, so this is going to be 10i. Then this is 2 to the power 3, which is 8, plus 6, which is 14, so this is plus 14j. And with that, we know that this is the position of the body when t equals 2 seconds. Okay, so the body is located at this point. Now we want to get the distance between the body and the girl. We know the girl is at the origin. So by that, we now say, thus, the distance between the car and the girl at this instant, between the car and the girl at this instant, at this instant is is given by, what would that be? So we draw our coordinate system again, which shows the floor. So this is our x-axis and this is our y-axis. This is where the girl is located. So girl is located here. Okay, so this is the girl's location, and from what we have just done now, we have seen that this is positive, this is also positive. So the x coordinate of the point where the body is located is 10 and the y coordinate is 14. So let's say this is 14 here and this is 10 here. That means the car will be located at this point at that instant. So this is the point where we have 10 comma 14, and all of those will be in meters, and then we need this distance. Of course, this is r, the magnitude of our position vector. So this length is the magnitude of our position vector at this point. So that is that about that. So this is the distance between 0 comma 0 of this coordinate system and 10 comma 14. So that should be quite easy to relate with. Okay, so therefore distance between the girl and the point is simply r, which is given by the modulus of r, which is simply the square root of 10, or if you like 10 minus 0 squared, plus 14, if you like 14 minus 0 squared. Distance between 2 points in the Cartesian coordinate system. You should recall that is the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay, so x2 is 10, this x1 is 0, 10 minus 0 squared, that gives us this. Y2 is 14, y1 is 0, that's 14 minus 0 all squared, so that gives us this as well. So with our calculator we can just solve this. This is going to be the square root of 10 squared plus 14 squared, and that gives us 2 root 74. We just need the number 17.20. Okay, so with that we have 17.20, so that is going to give us 17.20, which is in meters. So that is that about the A part. It is the distance between the girl and the car. So for the second part, it says, I mean for the B part now, it says the distance the car traveled in the interval from t equal to 0 to t equals 2 seconds. So we need to find out what happens between t equal to 0 and t equal to 2 seconds. We already found this position when t equal to 2 seconds. Let us find the position at t equal to 0. Okay, and then we'll come back to see what is the meaning of that distance anyways. So for the B part, we are interested in the distance traveled. Okay, so distance traveled is what we are interested in right here. Distance traveled by the body. We know distance traveled is denoted as s. Okay, from what we've done, that is the length of the path followed by the body. It is different from displacement. We have said distance is not magnitude of displacement in general. Okay. So if we wanted to get displacement, we know that will be given by delta r, which will be r2 minus r1. That is r, or the position when t is 2 seconds, minus the position when t is 0 seconds. Okay, so that would have given us the displacement of the body. But this question does not say we should get the displacement. If it asked us to get the displacement, we would proceed that way. But now we need to get the distance traveled. So the question is, how can we get the distance traveled in this case? We know that the body will generally move in a curved path, or say um, on a follow a curved trajectory or a non-straight line trajectory. So if it goes in a non-straight line trajectory, then we should be bothered about how to get the distance. So let's say, for instance, for illustration, please, this is not the exact position. We're not sure of what the exact path it follows in this case. I'm interested in that really. So we know this total length of the path followed by the body is what we will take as our S. So S is what we are interested in. And if it was displacement, that would just be a vector that connects these 2 points. And the magnitude of displacement obviously here is not necessarily equal to this S. So that is the idea. So how do we get S here? So to obtain the total distance, or the distance traveled by a body undergoing curvilinear motion, this is the process. We will take advantage of the fact that we know that speed, which is the rate of change in distance with respect to time, is equal to the magnitude of velocity. That means we will say, so recall, for instance, that speed v, which is equal to the s dt, is actually equal to the magnitude of velocity. So we can get the magnitude of velocity, for instance, and use that to obtain this result, okay, which will give us the speed. Okay, so that means we are very certain that the SDT, which is speed, is actually equal to the magnitude of velocity. Sorry, which is derivative of speed with respect to time is equal to the magnitude of velocity. And of course, we have found velocity vector already, so we can find the magnitude of the velocity vector. That should be quite easy to do. That will be the derivative of this with respect all of those derivatives that we have obtained already. Basically, and when we get the magnitude, that will just be equal to the square root of, we found it already, of course, x dot squared. This is in 2 dimensions, so it will just involve x dot squared and y dot squared. Of course, we know x dot is the x component of r, okay, when differentiated with respect to time. This is y component of r when differentiated with respect to time. When we take the square root of the sum of the squares of this, we know that will give us the speed, which is magnitude of velocity, and which is the rate of change in distance with respect to time. So that means from this we can see that our ds, okay, which is the differential change in the distance, will be equal to the square root of x dot squared plus y dot squared when we cross multiply, multiplying dt. So by this, we can obtain the distance traveled between two intervals if we integrate this with respect to time. We integrate both sides. This is a differential equation now. We know this will be a function of time. This will be a function of time. So we have separated the variables literally. So what we have there will then be integral of this will be equal to the integral of, so it will be the integral of the square root of x dot squared plus y dot squared, then with respect to time. So we differentiate it because this is a function of time, this is a function of time. So we differentiate integrate, sorry, this with respect to time. We'll also integrate this with respect to time. So we can say that change in s, so if we know the initial one minus this, so that is s2. So if we start from 0, for instance, this will be 0. So we just want to capture the distance, okay, from time t equal to 0. So at time t equal to 0, this is going from t equal to 0 to t equal to 2. So this is from t equal to 0 to t equal to 2. and that is the distance that we are interested in. So at the end of the day, when we integrate this, so this will always give us what we're interested in. So if we were going to take this, let's say from S2 to S1, the total distance traveled, then this will be T1 to T2. So this in general will give us the expression for distance traveled whenever we need to get distance traveled for curvilinear motion. So please take note of this in case you come across other issues like this, other problems like this. Of course, if this were in 3 dimensions, this would involve z dot squared as well. Okay. So basically for now, for the problem we have at hand, we just want to compare this from time t equal to 0. So that is 0, then this is s. Okay, that's what we want to get, the s. And then this is equal to the square root, sorry, the integral. So we have this integral, our t1. We're told that we should obtain this from t between the distance traveled between t equal to 0 and t equal to 2 seconds. So that means our t1 is 0 and our t2 is 2. So we will take our we'll take this integral from 0 to 2, and this will be the square root of, now we've obtained x dots already from the r that we have. We know that this is our r, this is our r, okay, this is our x dot, we've obtained that already, 4t, and our y dot is 3t squared, okay, from the differentiations we did up there. So this is going to be x dot squared, which is 4t all squared, plus 3t squared, then all squared. So we take the integral of this with respect to time, and we'll go from 0 to 2. It will give us the distance traveled. So this is s minus 0, which is s, the integral of 1. So this, you can say this is 1, for instance. Integral of 1 with respect to s, that is s, okay? And this goes from s to 0, so that's s minus 0. You could also write it as s2 minus s1 if you like. So it won't make any difference. That is just the distance that we're interested in. And this goes from 0 to 2. So what we need to do is to just integrate this for now. So from 0 to 2, let's tidy this up first and see what we get from that. This is going to be 8 into t squared. Okay, sorry, that's not 8, please. 4 squared, that's a 16. Then 3 squared is 9. So this is 9 into t to the power of 4. And then we take the integral of this with respect to t. So um, we need to integrate this, and to integrate this, the integral from 0 to 2, can we factor out anything here so that we can use the product rule of integration? So we can factor out t squared here. T squared is here, t squared is here. When we bring it out, that will be t. So we have here t multiplying the root of, so what we have left here will be 16. So this is going to be 16. Then this is plus 9t squared. Okay. So then with respect to time. So we can see, we can, for instance, think of a substitution to do here and insert the value. Okay, just go through the process and simplify this integral. But we can also just apply or just employ our calculator directly, and it gives us the results. Okay, so that's because that's available, then we can just use that and say, let's say this is integral, okay, of t. So we're just going to use x here in place of t, then multiplying the roots. So let's leave this anyways. Let's leave it without the simplification. That will be the root of 16t squared. So we have this 16 multiplying alpha x squared, then plus 90 cube, 90 to the power 4. That is 9 alpha x to the power of 4. Then that's all we have there. So put the limit to have this to be 0 and this to be 2. So let's see if our calculator can sort this for us. So it tells us we have 11.51. So that is 11.52 if you like. So in 3 significant figures. Okay, so we can just forget about this since our calculator can just solve that directly. So that tells us that the distance traveled that we're interested in is simply 11.52 in 4 significant figures, sorry, because the first significant digit here is 1. And that will be in meters. So this is the distance traveled, okay, by the body. So can we get the magnitude of displacement, they will probably be close but are not exactly the same. If you wanted to get magnitude of displacement, that would be final position minus initial position. We know the final position is the position when t is 2 seconds, and we obtained that here earlier. If we obtain the position when t is 0 seconds, that is not required. Okay, this is just for the purpose of check or just having fun with the concept. And if t is 0, this will be 2i plus 6j. So if we subtract the final position r, say r sub 2 minus r sub 0, that will be final position is 10. So this will be 10i. Okay, we're going to wipe it off. It's not required. So plus 14j minus the initial position, which is 2i plus 6j. If we did that, what does that give us? 10 minus 2, that is 8i, and then 14 minus 16, that is plus 14 minus 6, rather 14 minus 6, that is another 8. Okay, 8i plus 8j, and this is the displacement. So this here is delta r, which is the displacement. So if we needed to find the displacement delta r between the interval from t equal to 0 to t equal to 2 seconds, this is what we would do. And the magnitude of this displacement will be the square root of the square of 8 and the square of 8. So, and if we calculated that with a calculator, evaluated that with a calculator, we would obtain that is going to be, what does that give us? 8 squared, okay, square root of 8 squared plus 8 squared. That is 8 root 2, and that gives us 11.31. So we can see that it is very, very close to this, okay, almost the same. But this is much more than that. It is higher than it, okay. So it is very close. So if the time interval was shorter, very, very short, they will just be the same, okay. So, but that is that about that. Just know that this is the process to go through when you have to get the total distance traveled along a curved trajectory. So this is the process to go through. Take advantage of the fact that speed, which is the s dt, derivative of the distance with respect to time, or distance traveled with respect to time, is given by the magnitude of velocity. So we know the expression for the velocity, then we can get this by this integration. Okay, so that is that about that. We can now move on to consider the other part of this problem. So let us wipe this off. As I said, this is not required, so let us get rid of that. So the next part says we should get the speed and direction of the car's velocity at t equals 2 seconds. So we already know the expression for velocity. So we just substitute for t equals 2 seconds right here and see what that gives us. Okay. So let us get the velocity, and so we now say that at t equals to 2 seconds, v at t equals 2 seconds is what we need here. So we know that v from equation 2, we know what v is already. So we're going to make use of equation 2 to get v when t equals to 2 seconds. So no, from equation 2, we have the x component of v to be 4t and the other one to be 3t squared. So that is 4t and 3t squared. So this is going to be 4t, that is 4 into 2i plus 3t squared, that is 3 into 2 squared j. And this gives us 8i, then plus 2 squared, that is 4. 3 multiplying 4, that is 12. So this is going to be 8i plus 12j. So that is positive velocity at that instant. So we want to get the speed. Speed is magnitude of velocity. So we want to get the speed. We know that speed u is magnitude of velocity. So let's use u here, please, for consistency. Okay. Of course, it's not incorrect to write it as v since we use magnitude of velocity there. Okay. So we know that u, okay, which we have denoted as speed, is simply the magnitude of velocity, and that will be equal to the square root of 8 squared plus 12 squared. Okay, so when we take this, we will get our result for the speed at this instance. So the speed will be the root of 8 squared plus, so this is root of 8 squared plus 12 squared, and that gives us 4 root 13. Just want to get the number 14.42. So what we have here will be 14.42 in meters per second. No direction because it is just some magnitude. Okay. So you should get the speed at t equal to 2 seconds, we just did, which is magnitude of velocity at t equal to 2 seconds, and direction of the car's velocity at t equals 2 seconds. So how do we get direction? For us to get direction, we get orientation, okay, with respect to maybe the x-axis, okay, the horizontal axis in this case. Okay, so we can say that we know the x component is 8, the y component is 12. Both of them are positive. So by our coordinate system, that means x will be in this direction. So this is our x direction, and the component here is 8. This is our y direction, the component here is 12. So that means the velocity vector will be directed this way because it will be the vector sum of these two. So it's directed like this, and this is our velocity vector v at t equals 2 seconds. So with that, you can get the angle that it makes with the y-axis, we call it theta. Then we say that theta obviously is equal to the tan inverse of this side, which is 12, all over this side, which is 8. So we always have to draw this out. When we've drawn this out, or once we have drawn this out, it saves us from the stress of having to consider what will be the implication if this were negative or positive, because we'll already consider those the implications when we're drawing out these components. For instance, if the x component was negative, then we would not direct it this way, we would have directed it backwards, and then this velocity will have gone this way. So that helps us capture how we orient the velocity vector. Okay, so let's get the tan inverse of 12 over 8. So with our calculator, sheet and tan inverse of 12 divided by 8. So we close that bracket, and that gives us 56.3. So basically, this is equal to 56.3 degrees. And therefore, we say that the direction of velocity, okay, say v is at 56.3 degrees to the x-axis, the positive x-axis, okay? So to the positive x direction. So that is that about that. This is positive x direction, and the angle it makes with it is 56.3 degrees. So this is sufficient a statement to specify the direction of the velocity. So this is another part of our result, okay? And if the question asked us to just get the velocity, for instance, of course, as we said before, we could just leave it this way, or we would write it in this form where we write out the magnitude and also specify the direction. That is, if it required us to get velocity, we say that the velocity is equal to, what did we get the magnitude of this to be? 14.42 meters per second. That will just be 14.42 meters per second, and the direction is at 56.3 degrees. So we just indicate that this is some horizontal reference, and this will be at 56.3 degrees to that horizontal reference. And then that will be how we express our results in this case, because the motion is in the two-dimensional system, and we have defined for ourselves what clearly as provided in the question, we already know what are the x and y directions. Okay, so that's that, but that is not required. Okay, so that's about what is required of us in this problem. So let's go ahead now and consider the last part of this. It says we should obtain the magnitude of the car's acceleration at t equals 2 seconds. So that should be quite straightforward as well, because we know the expression for the car's acceleration as given by equation Roman figure 3. So we now say that for the D part of this problem, the magnitude of the car's acceleration will be given as follows. So for D, we need the acceleration at t equals 2 seconds. So how do we get that? From equation Roman figure 3, we can see that the acceleration vector at t equal to 2 seconds will be given by, so we just substitute t equals 2 seconds in that equation from our figure 3. This is 4I plus 60j, so that will be 4I plus 6 into 2j. So we have right here 4I plus 6 into 2, okay, j. And this gives us 4I plus 12j. So with this, we have the acceleration vector when t equals 2 seconds. However, as in the problem statement, we need the magnitude of the car's acceleration at that point. So we just get the magnitude of this. That is just the square root of 4 squared plus 12 squared. So therefore, acceleration at t equal to 2 seconds is just going to be equal to the square root of 4 squared plus 12 squared, and that gives us what we need. Let's write it out finally here. So let's employ our calculator again. This is the square root of 4 squared plus 12 squared, and that gives us 4 root 10, which is 12.65 in 4 significant figures. So this is 12.65 meters per second squared, and that is that about that. So can see that the problems are that easy. Once we know the definitions, we understand the terms, we know how they are related, then we're good to go. Okay. So the most important thing here, I would say, is the approach to getting the total distance traveled when we are analyzing curvilinear motion. Please, I need you to take note of this. Okay. So if you have problems like this, then you can solve them always using this approach. Once you have x and y, and also possibly z if it was a three-dimensional motion, so that is motion in space. In terms of t, then you're good to go. Okay. So thank you for watching. I'll see you in the next lesson as you consider other kinds of problems. Okay. Or another example on this concept. Okay. Thank you for watching.